Welcome to Brain Vision.
Okay, well, in this problem we have an air standard cycle with four processes. And in the first part of this problem, we have to draw the TS and PV diagram. So let's begin with this. Well, let's put here the axis for the PV diagram and for the TS diagram. So this is going to be the PV, and this one is going to be the TS diagram. Okay, well, the first thing we must remember is that this is PV, that for the PV diagram, the path for an isentropic transformation is described by a hyperbole. So we have here an hyperbole, which is going to be from points 1 through 2. And the second part of this process is a process with, let's call, is going to be a process with constant volume. So if we have a constant volume, the process is going to be this one, is a vertical straight line upwards. Okay, well, this is the point 3, and the process from 3 to 4 is another isentropic transformation. Therefore, we have another hyperbole curve. And the final process is a process with constant pressure, which is going to be this one. Okay, well, let's see. This is just the point 4. And here we have the isentropic curve. So this is the PV diagram. And we must remember that for a PV diagram, when we have the isentropic curve, isentropic transformation has no exchange of heat with the surroundings. Therefore, we have heat enter here and leaving here. Well, this is the PV diagram. Now let's see the TS diagram. For a TS diagram, we must remember that isentropic curves are represented by vertical lines. So this is the first isentropic curve, and this one is going to be the second isentropic curve. And the transformation with volume and pressure, with constant volume and constant pressure, is going to be this one. So we have our hyperbole here and another hyperbole here. This is the point 1, 2, 3, and 4. And these two vertical are the isentropic transformations. Okay, again, the heat enters here and leaves in here. Well, this is the item A of this problem. Now let's see item B and item C. Item B is a little complicated to solve. We want to find in item B what is the net work of this process, of this cycle. And we must remember that net work is just the input heat minus the output heat. It's just the difference between the heat that enters with the heat that leaves the cycle. So, to solve this problem, let's have the mindset that if we have one variable, we can find all the other variables just looking into the table of the book. So, we just need to know that the input heat is going to be the change in the internal energy, so it's just U3 minus U2. and the output heat is going to be the change in the enthalpy. And that's because, as we can see, the output heat, which is the second red arrow here, we have a constant pressure transformation. And constant pressure transformation means this is an enthalpy. So the energy is the enthalpy. Okay, so let's begin with point 1. Therefore, we need to find what is the internal energy in points 3 and 2, and the enthalpy in points 4 and 1. So let's begin with point 1. In point 1, we know that the initial temperature is just 295 Kelvin. Therefore, if we look in the table, we find that the enthalpy with this temperature is going to be 295.1 kilojoules per kilogram. Okay, and we also know that the relative pressure in point 1 is going to be 1.3068. Okay, so we already have the uh, first incognito, first variable, which is H1, the enthalpy in point 1. Now let's move on for point 2. In point 2, well, we don't have anything, but we can find one of the informations of the table. And the information we're going to find is the relative pressure on point 2, because this is just P2, P1, that multiplies PR1. Therefore, this is just 600 divided by 100 times 1.3068. Therefore, we have a relative pressure of 7.841. And with this relative pressure, we managed to look in the table and see that the internal energy in point 2 is 352.99, and the temperature is just 490.3. Okay, now moving to point 3. What we have in point 3? We have the temperature again. So 1500 Kelvin. And with this temperature, we can find that U3 is going to be 1205.41, which is what we want. And again, the relative pressure is going to be 601.9. Well, what else do we need? We can also find, using the ideal gas law, the pressure 3, because we have everything else. We have the volume, we have the temperature. Therefore, the pressure on point 3 is going to be 1853.6 kilopascal. And finally, at point 4, what we want is the enthalpy. Therefore, let's find the relative pressure. So the relative pressure is just P4 divided by P3, PR3. This is just 32.79, which means that the enthalpy in point 4, looking in the table, is going to be 739.71 kilojoules per kilogram. Now, finally, we can calculate everything that we want. Therefore, the heat output is going to be 739.71 minus 295.17, which gives us 444.5. And the heat input is going to be 1205.4 minus 352.29, which gives us 853.1. Therefore, the network that we want is just 408.6 kilojoules per kilogram. So this is the item B. And finally the item C. Item C, we need to find the efficiency of this cycle, this power cycle. So item C, we want the efficiency. And the efficiency is just the network divided by the heat input. Therefore, this is simply 408.6 divided by 853.1, which gives us an efficiency of 47.9%. And that's the final answer to this problem. Thanks for watching.